Yeah, I apologize.
Surprise, everyone, me again. Delighted to be back with you to kick us off.
You already did that one.
We already did that one. We're all set. So, no time travel today. Today, I'm delighted to introduce you to this panel, which is a continuation of a conversation that we started about 3 weeks ago at the Analog Astronaut Conference out at Biosphere 2 in Arizona. I'm going to turn you over to Jenny, our moderator for this panel, in just a moment. But this is actually an active session. So what I want to invite you all to do is, as you are listening to this conversation about the potential for using the ISS as an analog for the transit phase between Earth and Mars, keep an eye over in this corner of the room, which is where I'll be standing. And if you look over in that direction, you'll see 3 boards posted. One of those boards is labeled obstacles, one is labeled opportunities, and one is labeled offers. And what I will have back in the corner with me is a whole bunch of pens and sticky notes for you to be capturing your thoughts about particularly the opportunities and the offers that you and your community can make in order to get this really exciting analog opportunity off the ground. So Jenny will occasionally remind you that I'm back there. Feel free to get up while our friends are talking and come capture your points. And don't forget, if you want us to follow up with you, you need to give us your contact information on your sticky note as well. So I'll be there. Jenny, would you take it away?
Yes, thank you so much, Tiffany. So good morning, everyone. Thank you so much for being here for this panel. First, I'd like to introduce the panel members. First, we have Dr. Sian Proctor. She is an inspiration for Astronaut, a geoscientist, a STEAM communicator, and Dr. Shawna Pandya, physician, aquanaut, and soon to be flying as an astronaut for Virgin Galactic. And we have Dr. Michaela Musilova, astrobiologist and analog astronaut with a record-setting 30 missions. And I'm Dr. Jenny Hesterman. I'm a retired Air Force colonel, and I'm also an analog astronaut. Does anybody not know what an analog astronaut is? Okay, so let me go ahead and give a definition. So we perform experiments and science and research in spaces that are analogous to space. So basically caves, lava tubes on ice, in remote situations. Right now there's actually an isolation experiment at Lunaris, which is a moon analog in Poland. We have a crew in there for 30 days isolated. So that's what we do. We test things. We test everything from human factors to actually testing equipment for space, and we're available to you. If there's anything that, and I just being here over the last day and a half, I've been taking notes on things that we can do in our community. So Sian and Jazz Purwal, one of our colleagues, have put their arms around this community in the last couple years to professionalize what we do and really make it rigorous and not just space camp. And so we are performing rigorous research. We now have a journal. We have the world's biggest analog happening in October, where analogs around the world will simultaneously be performing missions. I'm the chair of the International Guidelines and Standards for Space Analog Committee. We now have a standard for space analogs, and there's more space analogs coming online. So thank you for letting me share that with you. So this is a continuation of a conversation that we held a few weeks ago at the Analog Astronaut Conference, which is held at Biosphere 2 in Tucson. And the Analog Astronaut community and Explore Mars came together to collaborate to pose a bold question. How can we use the ISS, which we know will not be in commission very much longer, how can we use it to replicate the transit time to Mars, which a few of the panels have talked about the challenges and opportunities that we have related to that. And yesterday, Vanessa Weiss said that the ISS is a space analog. So we got together and we talked about this, and I just want to do some of the takeaways here. I think the first thing, and the panel this morning said that the only thing that's not really replaceable on these missions is the human. And so we realized on the panel at the Analog Astronaut Conference that when the astronauts get to Mars and land, there's no one there to open the hatch for them. There's no one who's cooked a meal for them. Their habitat is not ready for them to live in unless we're able to send robots to do that first. So they need to be prepared. And so that was the conversation, was how can we use the ISS or other orbiting platforms, potentially a moon habitat, potentially bringing the astronauts back to Earth and putting them into a space analog. So that's kind of the basis for this, and we'll just go ahead and go right into the questions. And we'll just kind of do a round robin here. If you could fund or participate in one of these Mars transit analog missions, what would it look like? Sian, go ahead.
Yeah, I would definitely be participating. And so that whole idea of, going up to the ISS and living for maybe 6 months and then coming back to Earth and going immediately into an analog and then going again back to the IS for the 6 months and then return. That's what we're talking about. And when we're talking about simulating a Mars mission, right? And for me, what I envision is that you would launch to the ISS on one of the providers, and I've done it on SpaceX, not to the ISS, but to low Earth orbit. It's pretty awesome, and live there and do all this amazing work on the ISS. But the main thing is that when you come home after long duration space flight, how do you, if we're going to go to Mars, get out of the capsule like you said? My ideal situation would be, you splash down, you're in a SpaceX Dragon capsule after coming back from the ISS, and they hoist you up onto a boat, the return capsule retriever, just like they did for us and all of the other missions. But I don't know how many of you followed FRAM-2, the mission for FRAM-2, that was the first polar orbital one. They came back after 5 days, and their task for the first time ever was to get themselves out of the hatch, open the hatch and get themselves out of the capsule. But the longer you stay in space, the more challenging that is to be able to do that. So in my situation that I would love to have is that we would egress out of the capsule on our own, and then we would either immediately go into an analog on that ship, or we would work our way from that ship to another vessel that is next to it, and we would go into a simulation, and we would be on this, do an analog that is a sea analog for 4 months, 6 months, however, to replicate being on Mars. I mean, you're on the water, but you'd be isolated and confined. And you would do your egresses. They would be going underwater and being an aquanaut. And then after that, you would go back to Kennedy Space Center and launch back to the ISS. I think that's one of the easiest ways we could set up an analog where they go directly from splashdown into the sim versus having to be transported back to land and have to go into a building. But I would love to do that. So if anybody wants to help work on that, I'll take it.
Great, okay. Shawna, what do you think?
Yeah, that's a great question. So hi, everyone. I'm Shawna. I did not get the black jacket memo, apparently. So in answer to Dr. Jenny's question, that's fabulous. So I would posit this takes place in a two-part way. And the reason I'm going to present this is because our job in teasing out the nuances of what it's going to be like to send humans to Mars is, first of all, to identify and mitigate risk. And then the second part of that is to do no harm above all else. And in fact, I'll reverse the order. Firstly, and I'm a physician speaking from a medical perspective, whenever we treat someone, first and foremost, we do no harm. So how do we do that? I'm going to take Sian's idea and I'm going to build on it. So I completely agree with using the ISS to simulate that 6 to 9 month transit time. You want to know not just how to perform on your best day, but how to survive on your worst day. So you absolutely want to emulate the microgravity, the way microgravity wreaks havoc on your body. And so for those of you who don't know, quick physiology lesson on what space does to you. If you say you learn nothing else about space medicine from this panel, it's simply that space is trying to kill you. Okay, so the quick summary of that is your bones are going to lose density, your muscles are going to lose mass, your fluids are going to shift upwards, your brain may not like that, your optic nerves might be swollen from that increased pressure on your eyes, you might have vision shifts. That's what happens, we know that from ISS. There's countermeasures to help mitigate some of that, but not all of that. Okay, so now you're slightly decompensated. You can't quite, we know after 5 days, it's disconcerting enough to deal with that re-entry motion sickness. Try to extricate yourself from a capsule and then get to work. So the first thing you want to do is mimic that discomfort and that physiological shift that happens in transit to Mars. So then how do we take that one step further? We need to safely emulate the partial gravity environment of Mars. So 38% on Mars is what you're contending with. So this is where you and I differ a little bit, Sian, is because you're talking about going into an increased gravity well, which, does make it harder, but we want to know that what is that difference in going from microgravity to 1/3 gravity? And so first of all, this is where the do no harm proposal comes into effect. You come back to Earth, but then you're immediately put into gravity offset. Okay, so gravity offset is a harness that allows you to offload a certain percentage of your weight. So if you want to emulate microgravity like in ISS conditions, you offload 99% of your weight, you're weightless. If you want to emulate Mars conditions, you offload approximately 62% of your weight, and then you can emulate Martian gravity. And so then what does your body do when you offload the weight-bearing bones and muscles, the core muscles, the spine, the femurs, and how do you perform in that environment? And the reason I propose coming back to Earth, this is where I depart a little bit from where I said in Arizona, is because you also want to keep people safe. So if they're truly so decompensated that they're helpless little astronauts cannot fend for themselves, you do not want to find that out on Mars. You want to put that in a very closed, supervised environment where if they truly are in extremis, in distress, you medical aid, the crew, the backup crew, the supervising team can intervene, okay? So step one, do no harm, make sure it's safe to go from total decompensation to total independence in a simulated partial gravity environment. And again, those of you who know the more technical aspects of this know that, well, are you truly going to be in a gravity offset 24/7 for a 3-year mission profile? Probably not. Okay, but you're going to get as close to that. Maybe you can do periods of bed rest studies in between, but again, that's not a perfect way to emulate reduced gravity, okay? But at least you're kind of trying to put the bits and pieces, throw back to the first panel from this morning, trying to start to identify those unknown unknowns, okay? So checkbox 1, do no harm. So then now this is where we get to what Dr. Jenny was talking about in your introduction. So going to Mars right now is akin to going on a very long journey. You're dusty, you're tired, you're cranky. No one has made the beds. No one has opened up the inn. No one has made the meal. You've traveled all this way and check-in is not even ready. Okay, so that's what you're facing. So before you do that to Mars on this minimum 400-day mission profile, that's what's out there in the NASA literature, but most profiles are about 900 days. So minimum 3-year mission profile, why not go to our next nearest nearby partial gravity environment? And this is where we talk about analogs, which right now are deep space. Go to the moon, okay? Because the other thing that we don't know is the gravity prescription. What amount of gravity will be enough to mitigate all these deleterious physiological effects? Because we don't know what amount of gravity for what exposure, for what duration, what frequency will be enough to mitigate that bone density loss, that muscle mass loss, those fluid shifts, the immunological shifts that we see. That's a big question mark. 1G, good, 0G, bad. That's about all we know at this point. So once we have identified risks, the do no harm part, the next phase of that is to come back to ISS, emulate those transit times, and then go to the moon for the duration of a Mars mission, and then say, okay, look, if we run into trouble, at least medevac or immediate evacuation is days away, not 6 to 9 months away if you have a favorable launch window, or never if you have no favorable launch window. The solution for Mars, for medevac right now, is don't send your favorite astronauts.
Okay, that's not a good solution. Michaela, what do you think?
I think both are excellent points. I think ultimately it comes down to budget, and what are the different goals you want to achieve? Because Shawna's idea is great, but that is much further in the future. I feel we have to go through a few steps before we can get to an ideal scenario where we're using the moon as kind of the middle section between the ISS days. And, ship would actually be something in the earlier stages that, in terms of like affordability and practicality. And if we want to go even maybe a layer lower, there are a lot of existing analog stations around the world that could be used. But then, yes, there's the question of how do you transfer them from where they land from space to this existing analog facility, which would inconvenience a lot of things and complicate things. So that's one thing, is to think about, what is our budget and timeline? And per Shawna's point of health and safety first, we want to start with something that's feasible and safe, and that we've already tried before to some degree, so that we're not going to put the astronauts at huge risk. And then when we learn lessons from that, we can slowly upgrade to the better things, hopefully, of course, budget and other things favoring that. And so if we're looking at the very early stages of things, I would say also think about what is our goal? Like, what are we really trying to study? So, for example, with these two situations we have, on the ship, we would have our gravity, but then at least we have the cool EVAs in the water using scuba gear and all that, so that already helps us test some things, even from like a medical point of view to a little degree. Of course, on the moon, we would be much closer to this difference between Mars and Earth. But for example, there are things that we can test here on Earth, whether on a ship or in an analog facility, that are also extremely important. For example, the fact that on Mars, the crews are going to be very isolated from mission control, even during the flight there. There's a period of time, I think it's about 2 weeks, where there's going to be zero communication between the crew and Earth. Also, they're not going to have real-time access to mission control, and I think it was pointed out during a panel yesterday that in mission control you have so many experts and so many things that are basically on call for the ISS astronauts. You're not going to have that on Mars. And so there's a lot of things I think we could test in the early stages of a much more simple, budget-friendly analog, again, depending on what we have available to us, where we could focus on the psychological effects of the comms delay or food things. We still haven't quite figured out the best strategy with foods for these long-duration missions, because there are those people that want to be efficient, and there's a lot of analogs that exist these days where they want to prepare food for the year or however long the analog is mission. Like, they already prescribe in advance what you're going to have for breakfast, lunch, and dinner, and you have to stick to that. But the reality is, and Sian, you were on one of those kind of analogs in the early stages where that's just not how humans work. We want to have variety. We want to be able to choose what we want to eat. And we heard in the earlier panel, it really, how we feel affects also how we perform, and that could compromise the whole mission. So my point is, I guess, depending on what's available to us, if we have to go with something more simple, at least we can focus on some of these areas that we're still far behind in research, communication, food, even other medical factors and things like that, and then hopefully with time upgrade to something that's more realistic.
Okay, thank you.
Jenny, let's
Yes.
poll the audience
Okay.
on what they think, based on Michaela's ideas we should be looking for.
All right, fantastic. I don't think I have the changer to put the... Okay, awesome. So we're going to do a really fun thing that Tiffany brought out to the Analog Astronaut Conference for us that we loved. And there will be a QR code for you to scan with your phone and answer this question. What is the biggest current gap in Mars mission readiness that analogs could help fill? So go ahead and use the slider.
While the audience is answering this, I would like to just throw out there, we know AI and robotics is coming down the pipeline quickly. How realistic is it that, if we're going to do an analog, and when they come back from the ISS, where it's here on Earth, but it's your robotic assistant that opens up the door and right?
I love it, yeah.
And welcomes you. And then if you can't get, you need assistance getting out of the habitat, they help you. And I could see us working towards a modern day analog habitat that where we're testing the robotics and the, I guess, androids that we would potentially send to Mars ahead of time and see how humans interact with them and they interact with humans as part of the analog for figuring out, instead of having it happen on Mars, we would do that here. And it would be a big part of, because we know this stuff is coming down the pipeline, how do we design for that now?
I think that's really important because, well, anything we send to Mars, we need to test it a million times on.
I know,
first.
and especially the robotics and the AI.
Yeah.
Right? We don't want a HAL incident, you know.
So I think the robotics would really help, but also, we mentioned AI. I mentioned the situation with not having mission control ready to hand. And I think it was even mentioned during a panel recently that why not have AI substitute mission control to some degree. Of course, they can't compensate for all the brilliant minds that are in mission control, but maybe with time we could train them to at least help in some way. So yeah, there's a lot of ways we could use artificial intelligence, robotics, and things like that, and test them during these analogs first.
May I respond?
Of course.
So let me paint a picture of what we're trying to do when we go to Mars. So dating myself a little bit, but when we were watching those talent and variety shows back in the 80s and 90s, you'd see these talented plate spinners, and they would set up a pole and they'd start spinning a plate, and then they would do another one, and they'd do another one, and sometimes they would get up to 15, and the challenge is to keep spinning them and not drop the plates and break them, okay? So now you are the new NASA administrator, and here is your budget plate. You're spinning it. Here is your technology plate. Here is your keeping humans happy, healthy, performing plate. Here is the enabling technologies like AI. But now you're going to start greasing the floor with, soap, so you have to try not to slip as well. So that's your mass and budget and volume constraints. And then you're adding the environment. So these are these secret trap doors that secretly open up as well. And they open up not to alligators like we had in the first panel, but sharks with laser beams. And that is your radiation and your microgravity environment and isolation confinement. So translating this stressful picture, because I hope you're stressed getting this picture, I want to talk about the trade-offs that we have to make, because in an unlimited world, in my perfect world, you brought me back down to earth a little bit, Michaela, in saying that we have to think about budget. I try not to think about practicalities. It makes me less stressed. So try not to think about budget. But once you do, then you have to start thinking about the finances, the mass, the volume. And so then this is where the technologies we bring with us are limited by the mass, the volume, the power consumption. So yeah, we can bring androids if mass and constraints and budget isn't a consideration. We can bring all of them. We could do 16 staged missions ahead of time and create the Ritz-Carlton on Mars. That'd be nice. I'd love that. But we don't necessarily have that. And then we further constrain ourselves with the environment. So the challenges about AI specifically, this is a very long lead up to talk about AI, you're welcome, is there are massive data transfers involved with AI. The current comms architectures for Moon and Mars don't support that. So then how do we propose bringing AI, which I completely agree is a mandatory enabling technology for things like early warning diagnostics, diagnostics when you may have just one physician or crew medical officer, or the crew medical officer is the one who's downed, just-in-time training, guidelines and updates. So there's different models of AI that look at reduced or compressed data sets, so sending the node of skill sets like you might in a federated learning model, using transfer learning, which may be trained on smaller data sets. But then this is where the environment comes to stress you out, because even if you have the perfectly trained model, which it's not, it's only going to be trained on all the spaceflight physiology data that you have, which is an N of 700 that is very very diverse, heterogeneous mission profiles, 86% of which are mostly Caucasian males, and that includes the diaspora of commercial, traditional, Apollo, suborbital, low Earth orbit. And then on top of that, you also have to trust your AI model not to go into some sort of model drift. And then on top of that, if you have the perfect AI model, you have to trust it not to be disrupted by single event upsets, which could very well happen in the radiation environment. So Now, how do we feel about going to Mars?
Sign me up. But those are the things, we're already going down the pipeline, and we're talking, Mars is still years away. So how much are we going to be able to, if we imagine the ideal situation that we'd like to have for when we get to Mars, how do we create analogs and work towards testing that type of future here and now? And I think that that's more, we know the robots are being built. We know that the AIs and the models are being built. The question is, how do we take that technology that is already in play and start testing it towards this future when, you know, we do get boots on Mars, and how can we mitigate and say, yes, this is going to work, this isn't going to work, but to reduce that risk.
I agree. And I think it's interesting looking at the results of the Slido poll here that the psychological resilience and team dynamics was #1. And this is a very interesting, diverse audience of space professionals. So these are things we could test in the analogs, obviously, and we do test in the analogs. I was the commander of a mission at the Mars Desert Research Station, and we were all strangers, so 6 of us in a tin can in the middle of the desert for 2 weeks. That was a good test, and we succeeded, I'm happy to say. But also human physiology, and this is what we're talking about with microgravity, like how do we test that? And resource usage, food. We're doing a lot of interesting experiments in the analogs now with growing food. One interesting experiment, it wasn't mine, but we talked about what do we have an unlimited resource of when we're transiting to Mars, and that would be hair and nails continue to grow. And so someone in our community said, oh, maybe I can grow plants with hair and nails. And so we tried that, and apparently it was quite successful. So these are the kinds of out-of-the-box thinking things that we do.
I'll just quickly add to that. That was an experiment invented by Slovakian high school students.
No,
it's part of an initiative that I've been doing to educate young people around the world, but also allow them to be directly involved in international research. So it was a competition I designed back home. I'm from Slovakia originally. And high school students came up with this idea, like, why just throw away hair? Because we're going to have a lot of it over the long duration of a mission. Let's use it for something useful. And so we've been testing that at high seas for a long time.
So you need to take that.
I think that Sian does need to take this. Would you like to tell us why your phone is going off?
Yeah, it's going to be a good day. That was one of the songs for our inspiration for when I was driving up to the pad, that Haley and I. And the reason why I put it as my alarm to let me know that 11 o'clock, and I wanted to share this with all of you, is that at 11 o'clock on Instagram, the Smithsonian is announcing that my SpaceX spacesuit will be on display at the end of July. And I just want to say, as a little girl visiting, I'd always wanted to be a pilot, a military aviator, an astronaut. And I remember vividly visiting the Smithsonian Air and Space Museum as a kid with my family and walking through and just being in awe and wonder, but never, ever imagining that, I would do something that would end up in the Smithsonian. And it's the first SpaceX spacesuit that it will be on display. And so I hope you guys will, at the end of July, visit the Futures in Space. But also, at the end of our panel, go on Instagram. If you have Instagram, check out either my Instagram or the Smithsonian's and amplify, because I would love for people to know that this is happening.
And the first Black female pilot is now in the Smithsonian.
So
that's incredible.
As a result of the SpaceX Inspiration 4, I'm the first woman commercial spaceship pilot and the only African-American woman to be a mission pilot. So thank you, Shawna, for that. Thank you. Now I got to go and look at my phone while you're answering and share. I have to accept the collaboration invite.
So I think it'd be kind of interesting, Michaela, thank you so much for sharing where that idea came from. I didn't know that.
I feel like there's an obligatory Soylent Green joke that needs to be made there.
Okay.
About food being made at people. Or are we not going down that?
Absolutely. I think it'd be interesting for us all to talk about in our experiences, which I think between all of us, we have like 50 space analogs probably that we've participated in, from caves to all different situations. For each of us to talk about a experiment that we were part of or some research that we did that would actually apply to the transit to Mars. So Michaela, I'll start with you because 30 missions, leading missions at high seas, which is a habitat on a volcano in Hawaii. So maybe you could share with us.
Thank you. When I think about all those missions and all the experiences, it really always comes down to the humans. I could have a crew from all over the world and would be focusing on robotics or astrobiology, various things, but whether the mission failed or not was always down to the crew and how we interacted. And it wasn't just about having the most talented people that were well selected, but actually the more diverse the team was, the better the mission went. And I think it's because we're always learning something from each other, because we're different from each other. It helped create an environment of open-mindedness where people are like, oh, okay, yeah, we're different, we have difference of opinion, but that's not a bad thing, that's actually a very good thing. It also helped in situations when we faced some new challenge. Because everyone was from a slightly different background, they had different perspectives on things, and that actually helped us brainstorm and solve those problems more efficiently. So that was one thing. Diverse crew, emphasize empathy. The more empathy we use, again, the better we can resolve a lot of conflicts, the better we can communicate with each other. And I mentioned communication not just in the sense of like being polite and working together professionally, but being able to communicate how you feel and what you need to the others, which I think it was mentioned in the earlier panel, people are not used to being vulnerable, especially not in these sorts of situations. They're afraid of the consequences, what others are going to think of them. And so whenever I was the commander, I always tried to lead by example in that way. And when I was having a bad day or something bad happened, I even had a family member pass away while I was on a mission at one point. But I told the crew, I was always honest that, sorry, today is not my best day. Would someone mind helping me or taking over? And so to summarize, there's so much we can learn from these interactions. And I think we have so much to learn still to be fully prepared for Mars one day. And that's why, to your point earlier, Sian, analogs are a great place to do that. But like to try and do it really fully. So try and have the crew be in an isolated environment for a long period of time, ideally have the ISS factor in there, but the technologies really need to be something that we will actually be using on Mars. The AI being self-sufficient in terms of dealing with medical emergencies, again, just like it will be on Mars. So the more realistic we can make the analogs on Earth, the better we can test everything, including the human factors, and the more we'll be prepared. But if we don't invest that into the humans in particular, they will become the weakest link of the missions. And so we really can't underestimate that. And I fully agree with kind of the consensus of the earlier panel that we need to make sure the crew is not just surviving, but they're actually thriving in that environment, because then all the research will go well. They'll get along, they'll want to succeed in the mission, they'll help each other out, and they'll do a good job with the work that they're supposed to be doing.
Thank you. And I think emotional intelligence is something that we talked about at the Analog Astronaut Conference. I did a session on that because I think it's really important. Obviously, you need to be physically fit when you take off and land, but in between, when you're floating, it's really what's between your ears that matters the most, right? And a lot of that is emotional intelligence, the empathy, reading the room, understanding when you're the problem, things like that. So thank you so much. Shawna, what would you say in all of your experience would be most likely used in this transit to Mars?
Yeah, that's a great question. And before I answer your question, I'm just going to be a little bit heretical and disagree lovingly but respectfully with the poll results. I think you're all wrong. Because I think before you can answer any of the most challenging aspects, you actually need to, your biggest challenge is defining your mission architecture. And so what does that mean? That means Who are you sending? Why are you sending them? How many are you sending? How are they getting there? What is your mission profile? Are you doing a Mars flyby? Are you doing crew to Mars? Are you doing some crew in orbit, some to Mars? Because everything else trickles down from there. And this isn't just me. This is some entity called NASA. They have a lot of public documentation out there. It's fascinating. It's public domain, and it's freely readable, and it's really interesting to see what the thought process is, because are you sending 20 people? Are you sending 6 people? Are you sending 3 to orbit, 3 to land? Because that everything else, the duration, the resources, the ECLS flows down from there, and then once you've defined your mission architectures, or even if you have 2 competing architectures where the trade-offs are so close by razor-thin margins, that's where you can use your various test beds and analogs to discern which one may be the ultimate winner, or even make them more malleable or shape them a little bit more. So coming back to your other question about analogs and lessons learned, there's 2 answers to this. So I've been lucky enough to be part of 4 missions, 2 Mars simulations, 2 underwater aquanaut missions. And I've been lucky enough to test some really cool technologies that I really believe would enable humans on Mars. We know that the risk of skills deterioration is a very real risk. So practical example, you're the crew medical officer. The last time you stuck an IV in a patient was 9 months ago back on Earth. Next time you're called to use that skill is on the red planet. You've forgotten, you haven't practiced it in 9 months. Your poor patient is going to look like a pincushion. So my bad, sorry, I poked you 14 times. But you can use virtual reality to practice medical procedures, to retain that muscle memory, to retire risk. And the other benefit of virtual reality is that it is mass, volume, power constrained. You're not bringing a whole IV practice kit. You're doing that in the VR world. And so we've tested and launched and deployed virtual reality medical procedural modules, the world's first underwater demonstration of a teleradiology consult, where I, as the crew medical officer, met in a digital radiology reading room with the head of radiology in Saskatoon, Canada, over 4,000 kilometers away. And in real time, we reviewed the consult and the findings on the imaging together of a simulated trauma patient. And if you have a Mars architecture, you can do that in an asynchronous manner. And then the last way we used extended reality was using mixed reality, point of care ultrasound, again, to abide by those mass volume power constraints, but also give yourself a powerful imaging tool. So last thing I'll say, so I don't go on for too long, is echoing Michaela's point, is that, and also a callback to a point that Kaylee Stabino made on our first panel, is that sometimes the best discoveries you make are the unintended science or realizations that you get. And to Michaela's point, the biggest insight I got from these missions is that the crew dynamics 100% is the determining factor of make or break for mission. And then the other corollary of that is that crew training starts a year, a month before the mission. Like, you need to form, norm, storm way ahead of the mission so you can perform when you are in that tin can. And so the best crews, the ones that I still keep in contact with daily, are the ones that we have known for years and that we know how we act on our best and worst days. And that's what's made the best missions, because there's a joke about analogs: you either become best friends or you never speak again. And I'm happy to say that there are some who have become like family to me.
Fantastic. Okay, thank you. Before you go, Sian, I just want to remind everybody of the obstacles, offers, and opportunities board that we have back here. And Tiffany's back here. And as you're thinking through all of these things that we're talking about, later, if you want to write on a sticky note, and please put your name on there so we can respond to you of any of those 3 categories. Thank you. Sian?
Yeah, I agree with everything that's been said so far. I was very fortunate that I was in the very first high seas mission on the Big Island of Hawaii, and that was back in 2013. And so it was over a decade ago. It was funded by NASA to investigate food strategies for long duration space flight. And just to put it in perspective, this was funded by NASA to do that. And I lived in that high seas habitat for 4 months, investigating food strategies, because food is so important to overall not just health, but also mental health and mood. And so I think that when we're thinking about food for Mars and the transit, it's really important. But one of the things that I want to jump on is what you were talking about with virtual reality and augmented reality. As an artist, that's an area that I do a lot of work in. And I think that that's technology that's only going to get better in aiding how we learn, and not only learn and continue to be competent on the mission objectives and possibilities and contingencies and things like that, but also, we don't often talk about this, but entertainment, mental health, and how you can maintain mental health through those kinds of technologies, where you could potentially have your house in a VR. And so if you're feeling homesick, you can go in and you can walk through your living environment, and you could potentially interact with your loved ones in this VR space and maybe be able to mitigate that. You can go in and meet with, a psychologist or a psychiatrist through those types of interactions. You can practice meditation and breathing. You can play sports within a VR environment. And so there's so much potential there when I think about the health and well-being of the crew, particularly the mental health that, and again, these are that technology can be brought into the analog. I lived in Lunaris in Pila, Poland for 2 weeks, and this was back in 2017, and I had a headset, and it was and a breathing device. And when I was in the VR, you had to blow on this device and make this tree grow to find cosmic zen. And as a way of relaxing, and the technology again is only getting better to be able to help with some of those things. But by far, nothing beats crew cohesion and the ability to communicate. Training for, we trained for 6 months for the Inspiration 4, which was 3 days in space. And this whole idea of being comfortable with being uncomfortable. That's what my commander, Jared Isaacman, would often say, because you're in a closed environment on that spaceship for a long time. And we didn't go to the ISS. We lived, worked, and played in the Dragon capsule for 3 days. And we were the first crew to do that for stay and live in the Dragon capsule. And you don't have a lot of space. It's not, this is more space than in a Dragon capsule. And you really have to bond as a crew before that. You really have to be able to say, look, I can't, you have to be able to be vulnerable. I remember when we were hiking, Michaela is an amazing hiker. She's doing the 7 summits. She's done 4 of the 7 summits. And we'll be doing Everest next year. But we had to hike Rainier. I did not make it to the top of Rainier, but if you watch the documentary, Inspiration 4, we all have our backpacks, but about an hour before we reached our Camp Muir, we stopped, and I'm sitting there, and I'm like, and Jared, if you know Jared, he's like a billy goat. He comes bouncing over, still happy. Leo, how's it going? And I'm like, I'm not gonna make it. And he's like, no, you're gonna make it. It's all good. And he's like, let me take your backpack. And if you watch that documentary, at the end when we get to the camp, he's got 2 backpacks on. Because I had to be vulnerable, be like, I can't make it. He's like, I got you as a crew member. And that's what we're talking about.
Mm-hmm. Absolutely.
Yeah.
Thank you. So one of the things we tested in one of my analogs was a baby seal, a robotic baby seal that would be like a pet in space. Mm-hmm. And it got to know you, and it interacted with you and all the crew. Not everybody liked the baby seal, so there were 3 of us who did and 3 who didn't. That was part of the experiment.
You didn't club it, did you?
No. But there was time with the seal, time without the seal. We were wearing a lot of fitness wearable devices, and they were testing our blood pressure. Did we like it? Did it lower our blood pressure? Did it help our pulse? All those types of things. It's kind of interesting. Okay, so we have 5 minutes left. So quickly, round robin, this is going to cost money, this analog, all this testing. Everything that we do costs money. And one of the big takeaways, I think, from this conference, the Analog Astronaut Conference, and what we're trying to do in the analog community is directly tie what we do to Earth, right? And I feel like in the past we haven't been great about this. So if we could just quickly go to each person here and talk about what these efforts towards this Mars transit mission, how can we tie that to Earth? And Michaela, I'll start with you.
Thank you. I think there's a lot of ways we can help Earth by preparing for Mars. Already when we think about how hard it's going to be to live on Mars, all those things we'll learn from that experience we can apply here. So some examples, for example, to grow something on Mars is going to be extremely hard. Currently the soil there isn't exactly designed for that, so we'll have to change it, adapt in different ways, create correct greenhouses and all these things. But all the lessons we'll learn from that, we can actually apply here on Earth, especially now with our changing environment. It is becoming harder to grow food in different parts of our planet. So if we can grow on Mars, we'll be able to grow here too. And instead of waiting for that future Mars mission and then learning from that, bringing it here, why don't we start doing that already? And by having something like this Mars Transit analog and even other analogs where we truly test technologies that we will be using on Mars or we hope to use on Mars one day, we can already start applying these lessons learned to our everyday lives. And so it could be growing food, but it could be all these different technologies, things we talked about, AI, VR. Yesterday, I think it was mentioned that nuclear fission is probably going to be the main way we're going to have source of energy for Mars. That could be greatly used on Earth too. So there's so many things that in preparation for Mars we can actually develop and use here on Earth much sooner than we might think. And I think that's probably one of our greatest return on investment on top of all the medical, psychological, and other things too.
Okay, thank you. Shawna?
I'm going to speak from the medical aspect. And so on my Aquanaut mission, my commander had this shirt, and it was such a great shirt, I had to go and buy it. And it was this umbilical going from an aquanaut, and then it continued on into an astronaut on EVA, and the caption was same, but different. And so that's how I've come to think about whether when I'm working in the emergency room in rural Canada, which I do every single weekend when I'm not traveling. I was on medical deployment in Ukraine at the start of the war. And I also do a lot of health tech innovation for space. And that's a guiding philosophy for me. Same, but different. Because they're all examples of remote, resource limited, and in some cases, isolated and confined environments. And some of the best innovations we can come up with to not, as we said in the first panel, meet the standard of care on Mars, but surpass it and set a new standard of care for Mars and bring that back to Earth. And we're already doing that with novel innovations like real-time teleradiology guidance for mixed reality point-of-care ultrasound, with increasingly portable, minimally invasive biomonitoring devices, and also looking at the confluence of technology. So these minimally invasive biomonitoring devices that can be, paired with AI, as well as novel biomonitoring parameters like skin galvanic conductance, voice analysis, to determine even newer methods for early warning systems. And so I would posit that we can take the best of what we've done in the most challenging endeavor humanity's ever undertaken, sending humans to Mars, and bring those innovations to help our most in-need areas in healthcare on Earth.
Okay, fantastic. Thank you, Sian.
Yeah, I often say solving for human spaceflight is solving for Earth. The argument of why should we go to the moon and on to Mars with humans when we can send robotics? And that the reason why is solving for human spaceflight is all about efficiency in food, water, energy, resource management, and waste management. What do we have problems with here on Earth? Food, water, energy, resource management, waste management. We don't know what the best energy for Mars is yet. That technology hasn't been built yet. We don't know what the best recycling system for for Mars is going to be yet, because we haven't built it yet. There are all these things. In order for humans to survive on Mars, we have to imagine and build the most best and efficient systems in all of these life support areas. And that innovation, that technology, that knowledge is all created here, and it is spun off to make us more sustainable and efficient over time. And I think that that's one of the message that we need to really emphasize. Why human spaceflight is important is because it solves in all of the major areas that we have issues with here on Earth, and it does it in the most efficient and innovative ways possible.
Absolutely. Thank you very much. And I think to close out, we're going to do one more Slido.
So before we let you go, we want to have another opportunity for you to share your feedback on what you've heard about in this panel. There's another Slido here. You'll see another QR code. This is going to remain active for several days, so don't spend the time in the next panel doing this. We want you to pay attention to what's going on stage. But during the breaks, as you get home through your travels in the next week, come back to this opportunity to share your thoughts with us about how we could turn these types of analogs into a reality to deliver value both on Earth and to the future of space missions for us. Don't forget, we've got those boards where you can put your thoughts on sticky notes if you like to do it old school. We're going to be moving those boards out into the foyer, so they'll stick around a bit as well during breaks, during lunch. You're welcome to make your contributions there. And I think that's all I've got as well. Jenny, anything to add?
No, thank you so much. Thanks for having us, Explore Mars. Thank you for a fabulous conference here today. And thanks to my amazing panel. Thanks to you, the audience.